Hello and welcome. Tonight we are going to drift into a story about time itself, the kind of story that bends, stretches, and curves quietly beneath our feet. Don't worry, I'll try not to make this too fascinating. After all, you came here for rest, not for a university exam on physics. Think of it as a bedtime journey through clocks, trains, starlight, and the gentle strangeness of relativity. Before we begin, take a moment to like the video and subscribe. But only if you genuinely enjoy these sleepy science stories. And if you're still awake at the end, I'd love to know where you're listening from and what time it is there. I always like to imagine these quiet tales floating across time zones, whispered in different corners of the night. Now dim the lights, maybe let a fan hum softly in the background, and let's ease into this journey together. Imagine a clock, not a digital one glowing blue by your bedside, but an old pendulum clock. Wooden case, brass pendulum, hands ticking forward with steady rhythm. Each tick seems the same as the one before it, each tock identical, as though time itself marches in perfect regularity. For centuries, that is how people thought of time: steady, universal, absolute. The clock on your wall, the clock in your neighbor's kitchen, the stars circling above, all part of the same cosmic rhythm. Time, they believed, ticked the same for everyone, everywhere. You drift now into that older world when Newton's laws held sway. Space was a stage, unmoving, eternal. Time was a single drumbeat, beating equally for all. The universe was orderly, predictable, a great machine ticking forward in harmony. But as you linger here, listening to the pendulum, you might begin to wonder, what if not all clocks agree? What if time itself is not absolute, but relative, flowing differently depending on how you move, how you stand, how you look at the world? It is a strange thought, almost unsettling, yet quietly beautiful. Time as something flexible, not rigid. Time as something lived differently by each traveler. Picture yourself on a train. The carriage sways gently, wheels clacking below. You glance at your watch, steady, reliable. To you, sitting still, the seconds march forward evenly. But to someone standing by the tracks, watching the train rush past, your watch is not ticking quite the same. It runs slower, its seconds stretched by motion. This is relativity's first whisper, that time is not a single rhythm, but many. Scientists still wonder at how best to describe this. Some say time dilates, some say clocks slow down. But the essential truth is simple. When you move quickly, your time moves differently than someone else's. Both are right, both are real, and yet you need not worry. At everyday speeds, walking, cycling, even flying in an airplane, the effect is so small you never notice it. Your tea cools, your heart beats, your days pass just as they always have. Only when speeds approach the speed of light does time's flexibility reveal itself fully. But the seeds of this truth lie here in the simple question: is time absolute? Must every clock agree? Or could the universe allow something stranger, a relativity of experience, a gentle bending of seconds? You drift now from the pendulum clock to a sky full of stars. Light travels down from them, steady beams crossing the void. But light, too, holds a secret. No matter how you chase it, no matter how fast you move, it outruns you at the same speed. That constancy forces time itself to bend, to adjust, to keep the universe balanced. And that is where relativity begins, not with complicated equations, but with a clock in the quiet, ticking in one place, and a question. Does it tick the same for everyone, everywhere? The answer, softly, is no. Time is personal. Time is relative. And the universe, it seems, is more flexible than the pendulum lets on. So rest in this first thought. The clock by your bed ticks steadily, yes, but elsewhere, in another frame, another motion, it ticks differently. And both are true, both are real, both are part of the same gentle fabric of space and time. The quiet ticking clock fades into the background, and now you drift into a small office in Switzerland at the start of the 20th century. Not a grand laboratory, not a lecture hall, but a modest patent office in Bern. The air smells faintly of ink and paper. Stacks of applications sit on wooden desks, diagrams of machines and inventions waiting for approval. And in the middle of it all sits a young man, hair a little unruly, eyes distant, mind wandering far beyond the walls around him. Albert Einstein. He is not yet famous, not a professor, not a celebrated thinker, not even particularly well known among his colleagues. Officially, his work is to review patents, to check the designs of electrical devices, gears, and circuits. But unofficially, his mind is elsewhere. As he flips through applications, he drifts into thought experiments, questions about time, light, and motion. You drift into one of those thought experiments with him. He imagines himself riding on a beam of light. What would he see? Would the wave of light freeze alongside him, unmoving? That could not be. The equations of James Clerk Maxwell said light must always move at the same speed. No matter how fast you chase it, it still outruns you, steady and unchanging. It is a puzzle that gnawed at him. If Newton's world of absolute time and space was correct, then chasing light should work like chasing anything else. Run after a train, and the train seems slower. Run after light, and surely it should seem slower too. But no, light refuses to bend, and so, perhaps, it is not light that must change, but our understanding of space and time. Einstein, sitting at his desk, begins to turn the problem inside out. What if time itself stretches to keep the speed of light steady? What if lengths shrink, clocks slow, and simultaneity dissolves? What if the universe is not built on absolutes, but on relationships? Scientists still wonder at how remarkable it was that these thoughts came not from a grand observatory or laboratory, but from a clerk's daydreams. In 1905, his miracle year, Einstein published 4 papers that would reshape physics. One of them introduced the world to special relativity. You drift now into the streets of Bern at night. Gas lamps glow, footsteps echo on cobblestones, carriages roll slowly past. And somewhere above, the stars shine, their light racing through space at 300,000 kilometers per second. Einstein walks these streets, his thoughts keeping pace with the light overhead. It is a gentle reminder that great ideas often begin in ordinary places, that questions about the cosmos can bloom while reviewing patents, or walking home from work, or watching a clock tower at dusk. That the mysteries of time and space are not locked away for specialists, but belong to anyone who asks the right kind of "what if?" So rest now in this image. A young man at a desk, pen in hand, mind wandering to the edges of the universe. He doesn't know yet that his thoughts will change how we see space and time. For now, he is simply curious, quietly following the trail of light in his imagination. And you too can follow it, drifting gently into the puzzle that began with a clerk in Bern and grew into relativity itself. The cobblestones of Bern fade, and now you find yourself gazing upward into the sky, where starlight travels endlessly. Here lies the root of Einstein's curiosity, the stubborn constant at the heart of relativity, the speed of light. Imagine chasing a beam of light. You run faster, faster still, until you approach impossible speeds. In your mind you leap, stretching forward, nearly keeping pace with the golden ray. Surely now, as you draw close, the light must seem to slow. Surely it should drift beside you, no longer racing away. But no. No matter how fast you chase, the light still pulls away at the same speed. 300,000 kilometers per second. 1 billion kilometers per hour. The cosmic speed limit, steady for everyone, everywhere. This was not speculation, it was experiment. Scientists had measured light's speed over and over, with ever greater precision. Whether it came from the sun, or from lamps in a laboratory, or bounced off mirrors in clever arrangements, the number was always the same. Light refused to behave like trains or horses or arrows, and this constancy posed a problem. If light's speed is always the same, then something else must bend to make room. Space, time, perhaps both. You drift now into a thought experiment. Imagine 2 observers, one standing on a platform, one riding a train rushing past. A flash of light bursts in the middle of a carriage. To the passenger inside, the light spreads evenly, reaching both ends of the carriage at the same time. But to the observer on the platform, watching the train rush forward, the light seems to reach the rear sooner and the front later. 2 different accounts, both correct. The only way to reconcile them is to let time itself shift, stretch, and contract depending on motion. Scientists still marvel at the simplicity of this. Einstein's genius was not inventing complicated machinery, but trusting the constancy of light and letting logic unfold. If light's speed does not change, then our assumptions about space and time must. The familiar absolutes of Newton's clockwork world dissolve into relativity. And yet, there is something soothing in this. Light is reliable. No matter how fast you move, no matter who you are, the beam reaches you at the same pace. It does not cheat, does not falter. The universe has at least one steady anchor, one constant woven into the fabric of reality. You drift now through starlight itself. Photons leave the heart of the sun, streaming outward across 93 million miles, and they still reach Earth in 8 minutes, steady and true. A beam from a galaxy billions of years away races through emptiness and arrives in your telescope exactly as predicted. Light does not waver. And so relativity begins not with uncertainty, but with constancy. The speed of light, a number, unchanging, unfaltering the compass by which space and time themselves must adjust. Perhaps tonight, as you rest, you can feel a comfort in that steadiness. The world may shift, time may stretch, space may bend, but light moves on, always at the same speed, always faithful, always constant. The stars above you shine not only with beauty, but with reliability. Their beams, like whispers from far away, remind you that the universe has rules, steady and soft, even if they surprise us. The speed of light does not change. Instead, everything else bends around it, a quiet truth, discovered by a young clerk in Bern, but belonging to all of us. The steady speed of light lingers in your mind, constant and untouchable, and now you drift into the gentler idea that surrounds it. Motion itself is always relative. Imagine yourself sitting on a train. The carriage hums quietly, wheels clattering on the rails. Outside, fields slide past, trees blur, clouds drift lazily. To you, sitting still, it feels as though you are at rest. The cup of tea on the table in front of you does not spill. The pen in your hand does not slide away. Everything inside the carriage is calm, orderly, steady. But to someone standing on the platform as your train speeds by, the picture is different. To them, you are rushing forward at great speed. Your tea, your pen, your very heartbeat are all being carried along, swept into motion by the train. Both perspectives are correct. Neither is privileged. Motion depends on where you stand and how you move. You drift now onto a ship at sea. Below deck, the air is still. A sailor drops a ball and it falls straight to the floor. The ship may be gliding smoothly across the water, but inside, the ball does not care. It falls as though the ship were standing still. This was Galileo's insight long before Einstein, that uniform motion cannot be detected from within. And Einstein took it further. If motion is relative, and if the speed of light is constant, then time and space themselves must shift to preserve that constancy. The rhythm of clocks, the length of rods, the simultaneity of events, all bend to accommodate relativity. Scientists still wonder how best to describe this strangeness without making it sound too alien. The truth is simple but profound. There is no absolute rest, no universal stage. You can only measure motion relative to something else. It's oddly freeing, isn't it? The universe does not demand a fixed viewpoint. It allows many. Each traveler carries their own frame, their own story, their own clock. None is wrong. You drift now into the sky, watching airplanes arc across the horizon. To passengers inside, the cabin is calm, drinks steady on tray tables. To you on the ground, the plane is rushing at hundreds of miles per hour. To someone on another plane, moving differently, the speed changes again. Motion shifts with perspective. And deep down, this truth prepares the way for relativity's softer revelations. If there is no absolute stillness, no privileged frame, then space and time themselves are flexible. They must adjust gently to keep the laws of nature true for everyone, everywhere. So rest in this thought tonight. You are lying still, perhaps, in your bed. To you, motionless. But to the earth, spinning at 1,000 miles per hour, you are moving. To the earth orbiting the sun, faster still. To the galaxy drifting outward in cosmic expansion, faster yet. All true, all relative. You are at rest, and you are moving. Both descriptions live side by side, depending on where you look. And maybe there's a quiet comfort in that. You don't need to cling to one fixed frame. The universe accepts all perspectives, all motions, all stories. The hum of the train and the sway of the ship fade. And now you drift into one of relativity's gentlest, but most astonishing whispers. Moving clocks tick more slowly. Time itself stretches, depending on how you travel. Picture two identical twins. One remains on Earth, living quietly, measuring days with the steady rhythm of sunrises and sunsets. The other boards a spacecraft and races close to the speed of light. Inside the ship, their heart beats normally, their watch ticks steadily, their tea still cools at the same pace. Nothing feels unusual. But when they return, they discover their sibling on Earth has aged years more than they have. The traveler is younger because their clock, their time, has run slower. This is time dilation. You drift into a simple thought experiment. Imagine a light clock, two mirrors facing each other, with a beam of light bouncing between them. Each bounce counts a tick. In the frame of someone sitting beside it, the light moves straight up and down. Easy, steady, regular. But if the clock moves quickly past you, standing on a platform, you see the light travel a diagonal path, longer than before. And because light's speed must remain constant, those longer journeys mean fewer ticks. The moving clock runs slower. Scientists have tested this not only with thought, but with experiments. In the 1970s, atomic clocks were flown on airplanes around the world, while others remained on the ground. When compared afterward, the airborne clocks had ticked slightly fewer times. More recently, Satellites orbiting Earth confirm it every day. Their clocks run differently than ours on the surface. Adjustments must be made so your GPS can guide you home. It is a law not only of imagination, but of reality. And yet, you need not worry about missing hours in your daily walk. At everyday speeds, the effect is too small to notice. A jogger's watch, a cyclist's stopwatch, a pilot's wristwatch, all tick nearly in unison with those on the ground. Only when speeds grow vast, a significant fraction of light's pace, does time's stretch reveal itself. You drift now into a starship, coasting near the speed of light. Inside, the crew lives normally. Days feel like days. But outside, galaxies slide by, ages pass, stars are born and die. The travelers live a brief voyage, while the universe outside races through epochs. Scientists still wonder at the deeper meaning of this. Is time itself slowed? Or is it simply experienced differently in different frames? The mathematics says both are correct, both descriptions valid. Relativity doesn't privilege one story over the other, and perhaps that is the quiet comfort here. Time is not fragile, not absolute, but flexible. It adjusts gently, bending so the universe can remain harmonious. The ticking of your clock is true for you. The ticking of another clock, rushing past, is true for them. So rest tonight in this thought. Time does not march with a single drum beat. It sways, stretches, and bends. It holds you softly in your own frame, while holding others in theirs. And whether you move swiftly or lie still beneath your blanket, your time is always yours, steady, personal, real. The twins fade from view, their clocks ticking differently, and now you drift into another quiet effect of relativity, one that pairs gently with time dilation. When objects move quickly, they appear shorter along their direction of motion. This is length contraction. Picture a train rushing past at near the speed of light. To the passengers inside, the carriages feel perfectly normal, long, spacious, unchanged. But to you, standing on the platform, the train looks slightly squashed, its length compressed by its motion. It is not an illusion. It is not a trick of the eye. It is the way space itself adjusts to keep the speed of light constant. If moving clocks slow down, then moving rulers must shrink. Time and space bend together, keeping the universe consistent. You drift now into a thought experiment with two observers again. One rides on the train, measuring its length with a ruler. The other stands on the platform, stopwatch in hand. Both are correct, both precise, and yet their measurements disagree. The faster the train moves, the shorter it becomes to the one watching it rush by. Scientists still wonder at how to phrase this so it feels less absurd. To say, things shrink when they move, sounds almost cartoonish. But the mathematics and the experiments confirm it. Particles in accelerators, moving near light speed, experience distances differently. Cosmic rays traveling from space down into Earth's atmosphere live longer, travel farther, because for them, the journey is shorter. Length and time contract and dilate together, weaving relativity into every corner of motion. And yet, for us in daily life, the effect is imperceptible. A car speeding down a highway, an airplane soaring at 900 kilometers per hour, they remain the same size, their rulers unchanged, their cabins roomy. Only as motion approaches light speed do the changes grow noticeable. You drift now into space again, watching a starship coast near the speed of light. To its crew, the distance to a distant star seems shorter, the voyage manageable. To those left on Earth, the journey spans centuries. Both are right. Both stories are true, told in their own frames. There is a kind of poetry in this, isn't there? That motion reshapes not only time, but space itself. That the universe is not rigid, but supple, willing to bend lengths and hours so that light can remain steady. And perhaps there is comfort, too, in knowing that your own world is far from these extremes. Your table does not shrink when you slide it across the floor. Your bed does not contract when you roll over. The laws of relativity hover in the background, gentle and unnoticed, their strangeness reserved for the stars. So rest in this thought. Motion is relative, time is flexible, and space itself is willing to soften, shorten, bend. The universe is not a stage of rigid planks, but a fabric that folds and stretches to keep harmony. Your blanket tonight feels steady, your room unchanged. And yet, beneath that stability lies a deeper truth. Space and time are not fixed, but fluid, carrying you gently in their weave. E equals mc 2. The rushing train fades into silence, its length gently contracted, and now you drift toward one of the most famous equations ever written. So famous it almost feels like a cultural symbol rather than a piece of physics. 3 letters, an equals sign and a square. E equals mc2. It looks small, even simple, but within it lies a truth so profound it reshaped how we see matter and energy. They are not separate things. They are 2 faces of the same coin. Imagine holding a stone in your hand. To you, it feels solid, heavy, inert. But Einstein's equation whispers that the stone is also a reservoir of energy, immense energy, hidden in its mass. That even at rest, every gram of matter holds the potential to become light, heat, motion. Mass is energy, slowed and stored. The formula says it clearly: E energy, m mass. C2, the speed of light squared, a huge number, the conversion factor between mass and energy. Even a small amount of mass, multiplied by the enormous square of light speed, equals an astonishing amount of energy. You drift now into the heart of a star. Hydrogen atoms press together under crushing gravity, fusing into helium. In the process, a tiny fraction of their mass is lost. It does not disappear. It transforms into energy, released as light and heat. That light streams outward, warms planets, and eventually touches your skin on a sunny afternoon. E equals mc2 is at work in every sunrise. The same principle explains why food sustains you. Chemical bonds hold energy, stored from sunlight that plants captured. You eat, and your body releases that energy, transforming mass into motion, warmth, thought. Scientists still marvel at the elegance of this equation. It is not only a tool for nuclear physics or astrophysics, but a unifying idea. The matter you see and touch is simply another form of the energy that flows invisibly. There is a gentleness in this, too. You are warmed each day by the quiet truth of mass turning into light in the sun. You are alive because plants have stored that light in their leaves, and you, in turn, release it slowly. Even your body, at rest beneath a blanket, radiates faint warmth, energy quietly flowing outward, mass giving itself back to the universe in whispers. Of course, E equals mc2 has its dramatic side. In the 20th century, it explained the power of nuclear reactions, the energy in both stars and weapons. But tonight, we dwell not on explosions, but on the softer truth, that mass and energy are never separate, that everything around you is part of a single exchange, a slow dance of transformation. So rest now in this thought. The chair that supports you, the blanket that covers you, the body that breathes, all are energy, hidden and humming, waiting to flow. Matter is not rigid, but potential. And perhaps, as you close your eyes, you can feel yourself as part of this equation too. A small amount of mass, filled with energy, glowing quietly in the night, connected to stars and stones alike by the same law. E equals mc2, three small symbols, one vast truth. Mass and energy bound together forever. The glow of Einstein's equation fades softly, and now you drift into the next stage of the story. Special relativity had shown how space and time bend with motion, how energy and mass are two forms of the same thing. But for Einstein, that was only the beginning. A deeper question remained: what about gravity? For centuries, gravity had been described as a force, a mysterious tug acting across space. Newton had captured it with clarity. Every mass attracts every other mass. Apples fall, moons curve, planets orbit, all under the same invisible pull. It worked beautifully, but Newton had not explained how the force was transmitted. He himself admitted, "I frame no hypotheses." Einstein, sitting in his modest study, began to wonder if gravity, too, might be woven into relativity. If motion can bend time, perhaps gravity can as well. Perhaps the two are not separate puzzles, but parts of one fabric. You drift now into one of his most famous moments of inspiration. Einstein later described it as the happiest thought of my life. He imagined a man falling freely from a roof. As he fell, he would feel weightless. Objects around him would float, just as they do in orbit. For those brief seconds, the man would not feel gravity at all. This was the seed of the equivalence principle, that free fall and weightlessness are indistinguishable. Gravity pulling you downward feels the same as being inside an elevator whose cables have been cut. Conversely, standing on Earth, pressed into the floor, feels the same as being pushed upward by an accelerating rocket. Scientists still wonder at the simplicity of this thought. It was not a complex experiment, not a huge calculation, but a shift in perspective. Gravity might not be a force in the traditional sense, but something deeper, an effect of how space and time themselves behave. Einstein began to dream of a new relativity, one not limited to motion at constant speeds, but embracing acceleration, gravity, the very geometry of the universe. It would take him nearly a decade to develop. Equations grew heavy, mathematics unfamiliar, nights long. But slowly he shaped a vision, gravity not as a force, but as the bending of spacetime itself. You drift now through this transition, from special to general, from motion alone to motion plus gravity. Special relativity was a brilliant lantern, illuminating time dilation, length contraction, E equals mc2. But general relativity would become the sunrise, reshaping our view of the entire cosmos. And perhaps there is comfort in Einstein's persistence. He did not stop at the first answers, dazzling though they were. He kept asking, kept imagining, kept letting thought experiments guide him, elevators, falling men, rockets. The great ideas often grow not from complexity, but from simple images held patiently in the mind. So rest in this transition. You have learned that motion bends time and space, that mass and energy are one. Now you begin to drift into the deeper dream. Gravity itself, not as a tug, but as a curve, a geometry in which you live every moment. From special to general, from simple to profound, Einstein's journey continues, and you float gently along with it. The quiet thought of transition lingers, and now you drift deeper into the image that Einstein called his happiest thought. A thought so simple that anyone can imagine it, and yet so profound that it reshaped gravity itself. This is the equivalence principle. Picture yourself inside a small elevator, sealed shut, drifting in the middle of space. Outside, there are no stars, no planets, no hints to tell you where you are. Suddenly, the elevator begins to accelerate upward. You feel pressed to the floor. A ball you release falls downward. To you, it seems gravity has appeared. Now picture the elevator instead standing still on Earth. You are pulled downward by gravity, pressed into the floor. A ball falls, just as before. The two situations feel identical. Without looking outside, you cannot tell the difference. This is the heart of the equivalence principle. The experience of acceleration and the experience of gravity are the same. You drift now into another thought. Imagine the opposite. A falling elevator. You step inside and the cable snaps. For those brief moments, You and everything around you float weightless. A ball released from your hand hovers beside you. It is not that gravity has disappeared, it is that everything is falling together. The sensation of weight is gone. Einstein realized that these simple observations meant something astonishing. Gravity is not a mysterious force tugging at you from Earth's center. It is indistinguishable from acceleration. And if acceleration bends time and space, then gravity must too. Scientists still wonder at how such a humble picture, an elevator, a ball, a feeling of weight, could lead to equations that describe the bending of spacetime, the orbit of planets, even the birth of black holes. But this is Einstein's gift, to take the ordinary and let it reveal the extraordinary. You drift now into space, watching astronauts aboard the International Space Station. They float, drifting gracefully from wall to wall, not because gravity has vanished, but because they are in free fall, orbiting Earth. Just like the elevator, they fall continuously, and so they feel weightless. The equivalence principle explains not only imagination, but real life above our heads. And there is something soothing here. Gravity, once seen as an invisible hand, becomes a matter of perspective. The same sensation can be described as acceleration in space or gravity on Earth. Different stories, equally true, both part of the same law. Perhaps you feel this in your own life, the way your body presses into the bed as you rest is gravity's constant presence, indistinguishable from the gentle acceleration you would feel in a rocket leaving Earth. The universe treats them as the same, two expressions of the same geometry. So let yourself rest in this thought. Gravity is not strange, not alien, but familiar. It is the press of the mattress, the fall of a ball, the floating of astronauts, the rising of a rocket. All the same, all equivalent, all gentle. The equivalence principle is Einstein's whisper. Gravity and acceleration are one, and through that unity, the door opens to curved spacetime itself. The quiet elevator fades, its walls drifting away, and now you step into the wider vision that grew from Einstein's happiest thought. If acceleration and gravity are the same, then gravity must not be a force pulling from a distance, but something subtler, the bending of space and time themselves. Picture a great fabric stretched out flat. Place a marble on it, and the fabric hardly moves. Place something heavier, a ball, and the fabric curves, dipping under its weight. Now roll a smaller marble nearby. It does not fly straight. It follows the curve, looping around the heavier ball, not because they touched, but because the surface beneath them was bent. This is Einstein's vision of gravity. Spacetime as a fabric, curved by mass and energy. Planets are not pulled by invisible strings, they glide along curves in the geometry. The Earth circles the Sun because the Sun bends spacetime, and the Earth follows that curve as naturally as a marble rolling in a bowl. You drift now into the solar system. The sun glows at the center, its immense mass bending spacetime all around. The planets follow smooth paths, not tugged by hands, but guided by curves. Mercury, closest in, loops slightly differently, its orbit precessing in ways Newton could not explain, but Einstein's equations described perfectly. Scientists still marvel at the elegance of this shift. Newton gave us precision, apples falling, moons orbiting, planets circling. But Einstein gave us geometry. The universe is not a stage with actors pushed and pulled. It is a flexible fabric, a canvas that curves, guiding everything upon it. Even light, though weightless, feels the bend. A ray passing near the sun does not travel in a straight line, but curves along the warped spacetime. In 1919, during a solar eclipse, astronomers measured starlight bent just as Einstein predicted. The world changed overnight. Newspapers declared, "Revolution in science, new theory of the universe." You drift now above Earth. Imagine tossing a ball. On Newton's stage, gravity pulls it downward. On Einstein's canvas, the ball simply follows the curve of spacetime Earth has created. Both descriptions work, but one is richer, softer, more complete. There is comfort here, too. Gravity is not a force acting at a distance, mysterious and invisible. It is simply geometry, the natural shape of the universe around mass. Just as a river carves valleys and guides boats, so does spacetime curve around stars and guide planets. And you, lying now under a blanket, are part of this curvature. The earth beneath you bends spacetime gently, enough to keep the moon circling, enough to hold you steady on its surface. You do not feel pulled downward by a rope. You feel the bed beneath you pressing upward, your body following the simplest curve it can in the fabric of space and time. So rest in this thought. You are not being tugged or held against your will. You are simply gliding along the geometry of the cosmos. Every star, every planet, every atom bends the fabric, and together they weave the soft, curved tapestry in which you live. Spacetime curves, planets follow, light bends, and you too rest gently in the fold. The fabric of spacetime stretches out before you, planets rolling gently in their orbits, and now you drift toward one of Einstein's boldest predictions. Even light itself must follow the curves. On Newton's stage, gravity pulls on masses. A stone, an apple, a planet, each with weight, each tugged by invisible force. But light, weightless, intangible, racing at the universal speed. Surely it should pass unaffected, gliding straight through the cosmos. Einstein thought otherwise. If spacetime itself is curved, then everything that moves within it must follow those curves, even light. A beam of starlight grazing the sun would not travel straight, but bend slightly, tracing the geometry created by the sun's immense mass. You drift now into 1919, a moment that confirmed this idea to the world. Astronomers prepared for a solar eclipse, when the sun would be hidden just enough to reveal stars near its edge. With careful telescopes, they measured the positions of those stars. And when the photographs were developed, the stars appeared shifted, not because they had moved, but because their light had curved on its way to Earth. The newspapers announced the result with dramatic flair. Lights all askew in the HEAVNS. Einstein, once a quiet patent clerk, was suddenly a name known around the world. His vision of curved spacetime had passed its first great test. Scientists still marvel at how light obeys this rule, though it has no mass. The reason is subtle. Light always follows the straightest possible path, a geodesic, through spacetime. But if spacetime itself is curved, then the straight path is not straight at all. It arcs and bends. You drift now through the universe, watching the effect unfold on grand scales. Galaxies act as lenses, bending light from even more distant galaxies behind them. The light stretches, twists, sometimes splitting into arcs and rings. Astronomers call it gravitational lensing. To the eye, it is beautiful. To the mind, it is proof that spacetime curves wherever mass resides. Even here on Earth, experiments have confirmed the bending of light by gravity. Signals from spacecraft near the sun arrive slightly later, their paths curved just enough to lengthen the journey. Tiny, precise, but always in harmony with Einstein's equations. And perhaps there is a quiet poetry in this. Light, once thought untouchable, yields gently to the shape of the universe. It does not resist, does not rebel. It flows along the curves, graceful as water in a stream. So rest in this thought. When you see starlight twinkling in the night, you are not seeing only the stars themselves. You are seeing paths traced through curved spacetime, beams shaped by suns, planets, and galaxies along the way. Every star you gaze at is a message, bent slightly but faithfully by the gentle curves of the cosmos. The universe does not shout its geometry. It whispers it in the bending of light, in the shifting of stars, in the quiet confirmation that space and time are not rigid, but soft, pliant, alive. And tonight, as you close your eyes, imagine yourself as one more beam of light, following a curved path through the fabric of spacetime, always steady, always graceful, always guided. The bending of starlight drifts behind you, and now you move toward the most mysterious consequence of curved spacetime. If mass bends space, and great mass bends it greatly, then what happens when mass collapses beyond measure? The answer is a place so deep, so curved, that not even light can escape, a black hole. Picture a star much larger than our sun. It burns for millions of years, fusing hydrogen into heavier elements, shining brightly across the cosmos. But one day, its fuel runs low. Fusion slows, pressure falters, gravity takes over. The star collapses inward, tighter and tighter, until all its mass is pressed into a space unimaginably small. The curvature of spacetime grows steeper, like a slope turned into a cliff. At the edge lies what scientists call the event horizon. Cross it, and all paths lead inward. Light itself cannot climb out. Time slows as you approach, stretching toward infinity. To an outside observer, you seem frozen at the edge, never quite falling in. But to you, inside, the fall continues, silent and unstoppable. You drift now near one of these strange objects. From afar, it looks black, invisible, outlined only by the glow of matter spiraling around it. Gas and dust heat as they fall inward, releasing light and X-rays, announcing the presence of something unseen. Some black holes are small, born of collapsing stars. Others are giants, millions or billions of times the sun's mass, anchoring the hearts of galaxies. Scientists still wonder about what lies inside. The equations point to a singularity, a point where density becomes infinite, where spacetime curves beyond description. But perhaps our mathematics falters there. Perhaps a deeper theory waits, one that unites relativity with quantum mechanics. And yet, even with mystery at their core, black holes are not only destructive. They shape galaxies, drive the growth of stars, sculpt the universe. Their gravity focuses light, bends time, and even allows us to test Einstein's equations at their most extreme. You drift further, imagining what it would feel like to fall toward one. The pull grows stronger, tides stretch your body in ways both dramatic and dreamlike. Time slows, the universe outside racing ahead while your own clock ticks gently, steadily. To you, the journey continues. To others, you fade into stillness. Two perspectives, equally real, written in spacetime. And perhaps, strangely, there is a kind of calm here. A black hole is not a monster, but a natural outcome of gravity's quiet insistence. Matter curves space. Enough matter curves it so deeply that even light cannot climb. No anger, no malice, only geometry. So rest now in this thought. The universe allows mysteries, places where our understanding falls short, horizons we cannot cross. But even those are part of the same law, the same gentle fabric of space and time. Black holes are not the end of relativity. They are its deepest whisper, the point where curved spacetime shows its full power, silent, steady, inevitable. And as you drift into sleep, you need not fear the pull. You are safe on Earth's gentle curve, far from such horizons. But you can let the image soothe you. A universe that holds even its extremes in silence, order, and calm. The silence of black holes fades, and now you drift outward again, away from singularities and horizons, into the grandest canvas of all. The universe itself. Relativity does not stop at planets, stars, or even black holes. It reaches to the scale of everything, shaping the cosmos as a whole. In the early 20th century, Einstein's equations hinted at something unsettling. The mathematics suggested the universe could not sit still. Space itself must either expand or contract. But Einstein, reluctant to imagine a changing cosmos, added what he called the cosmological constant, a kind of balancing term to keep the universe static. Later, when evidence emerged of expansion, he reportedly called that constant his biggest blunder. You drift now into the work of Edwin Hubble in the 1920s. Using telescopes at Mount Wilson Observatory, Hubble measured the light from distant galaxies. To his surprise, the light was redshifted, stretched, as though the galaxies were rushing away. The farther they were, the faster they receded. The universe was not static at all. It was expanding. Scientists still marvel at how profound this discovery was. Not only were galaxies moving through space, but space itself was stretching, carrying them apart. The fabric of spacetime, once thought rigid, was shown to be flexible, dynamic, alive. You drift through this expanding fabric now. Galaxies glow like lanterns, each carried outward not by motion through space, but by space itself stretching between them. The farther you look, the faster they recede, until at great distances, their light can no longer reach us. A cosmic horizon, drawn not by walls, but by the limits of spacetime's expansion. And if space is expanding, then long ago it must have been smaller, denser, hotter. The equations point backward to a beginning, what we call the Big Bang. Not an explosion in space, but an expansion of space itself, unfolding from a state of incredible energy and density. Even now, the afterglow of that beginning lingers. The cosmic microwave background, faint radio waves filling the sky, is the cooled remnant of a time when the universe was a sea of hot plasma. Billions of years later, it has stretched into near-uniform stillness, just a few degrees above absolute zero. Entropy, once again, written in the heavens. There is poetry here. The same relativity that explains a clock on a train also explains the growth of galaxies. The same equations that describe light bending near the sun also describe light stretched across billions of years. Relativity is not just local, not just small, it is cosmic. And perhaps there is comfort in this vastness. The universe is not shrinking inward, not collapsing in on itself. It is opening, expanding, stretching toward tomorrow. Galaxies drift apart like gentle ripples, each carrying its own story, its own stars, its own worlds. You drift now at the edge of this vision, gazing into the dark between galaxies. It is quiet, immense, but not empty. It is spacetime itself, expanding softly, carrying everything forward. So rest in this thought. The universe is not frozen. It is alive with motion, written into the very fabric of spacetime. You are not a static figure in a rigid cosmos, but a traveler carried gently on the currents of expansion. And as you breathe slowly, evenly, you echo that rhythm. The universe itself expanding, softly, patiently, carrying all of us with it into the thermal night. The galaxies drift outward, their light stretched across time, And now you return to something closer, something familiar. Relativity may seem vast and abstract, a story of black holes and cosmic expansion, but its effects touch your daily life too, quiet, hidden, but always present. Think first of satellites. Above your head, dozens of GPS satellites orbit Earth, each carrying atomic clocks. These clocks are precise, so precise that even the tiniest shifts matter. And relativity ensures those shifts are real. In orbit, the satellites are moving quickly relative to Earth's surface. Special relativity says their clocks should tick more slowly, but they are also farther from Earth's mass, where gravity's curve is shallower. General relativity says their clocks should tick faster. The two effects do not cancel. Together, they mean that without adjustment, GPS satellites would drift by nanoseconds each day. And nanoseconds matter. A single second of error would place you hundreds of kilometers away from your true location. Engineers must constantly correct for relativity, ensuring your phone can guide you home or to the nearest cafe with uncanny accuracy. You drift now into a hospital. Here, relativity hides in another tool, MRI machines. They rely on nuclear magnetic resonance, a phenomenon tied to quantum mechanics and relativity alike, allowing doctors to see the fine structure of tissues. Each image of a beating heart or a healing bone owes something to Einstein's vision. Even electricity in your home whispers of relativity. The electrons moving through wires, the magnetism in motors, the stability of matter itself. All are shaped by relativistic physics, woven into the fabric of technology so thoroughly that we rarely notice. Scientists still marvel at how a theory born from chasing light on paper can shape such ordinary things. Your map app, your medical scan, the circuits in your laptop. All tuned by the same laws that describe galaxies drifting apart. And relativity is not only in machines. It is in the sun's warmth each morning. Fusion in the sun's core relies on relativity to explain why particles can fuse, why light escapes, why energy reaches Earth. Without Einstein's work, the sun itself would remain partly mysterious. You drift now into your own body. Every moment, chemical reactions keep you alive, electrons bound to atoms by subtle rules of relativistic physics. Even your warmth, the quiet radiation you give off into the night, depends on the interplay of energy, mass, and light. Perhaps there is comfort here. Relativity is not distant, not aloof. It is the steady correction in a GPS satellite, the glow of sunlight, the breath you take. It is woven into your daily life, silently, gently, faithfully. So rest now in this thought, you are never far from relativity. You live within it, every moment, every step, every heartbeat. Time bends for satellites above you. Space curves beneath your feet. Light carries messages across the sky, steady and true. Einstein's equations are not only for textbooks. They are for your morning walk, your evening meal, your journey through life itself. And tonight, as you close your eyes, you can trust that the same laws guiding galaxies also guide the tools in your pocket, the machines in your city, and the very atoms in your body. The cosmos and the kitchen, the stars and your breath, all woven by relativity's soft, steady hand. The satellites, the maps, the sunlight on your cheek all fade now, and you drift into the final image of relativity, not as an equation, not as a theory, but as a place to rest. Because relativity, in the end, is not only about motion and clocks and light. It is about the fabric of existence itself, the stage on which you live every moment. Space-time. Picture space and time not as two separate things, one a backdrop, the other a ticking rhythm, but as a single fabric, soft and continuous. It stretches in three directions of space and one of time, all woven together. You are not standing in space-time, you are part of it, carried along by its curves. You drift now above Earth, gazing down at the planet. The ground beneath bends space-time just enough to hold you close, oceans flowing and moons circling in reply. Farther out, the sun bends space-time on a grander scale, guiding Earth and planets in their orbits. On even larger scales, galaxies sit in curved hollows, shaping the paths of stars and light. Everywhere you look, space-time is curved and alive, and through it all, time flows. Not absolute, not the same for everyone, but always personal, always true within your own frame. You tick forward at your pace, while others tick at theirs. Clocks disagree, but relativity assures us both are correct. Scientists still wonder at what lies beyond relativity, how it might join hands with quantum mechanics, what it means near singularities, what the universe's ultimate fate will be. But for tonight, you need not wonder. It is enough to rest in what relativity already tells us. You are held in the fabric of space-time, safe in its steady embrace. Imagine yourself lying on that fabric. It cradles you, bends around you, carries you forward. You do not fall off, you do not slip away. You are part of the weave, inseparable, continuous. And perhaps the most soothing thought of all is that space-time does not demand effort from you. You need not push to move forward in time. Each second comes, gently, inevitably. Each moment carries you further on, as naturally as breathing. So let yourself rest now. Your clock ticks at its pace. Your space curves softly beneath you. Your light flows outward into the night. You are not outside the universe, not apart from it. You are stitched into its very fabric. The pendulum clock in the quiet, the trains rushing by, the starlight bending, the galaxies drifting. All of them are one story, one fabric, one gentle relativity. And tonight, you can rest in it. And now the story of relativity softens into silence. You have drifted through clocks and trains, through bending starlight and curving space-time, through galaxies drifting outward on the expanding fabric of the universe. And what remains is not the equations, not the debates, but the gentle reassurance that the cosmos is steady, ordered, and kind enough to carry you within it. Take a slow breath in. Hold it softly. Let it go. Feel the weight of your body pressed gently into the bed. That sensation is gravity, the curve of spacetime beneath you. You are not being pulled down by invisible strings. You are simply following the softest path the universe provides. You are safe in that curve, held by the same law that keeps the moon circling, that bends the light of stars, that guides galaxies on their endless drift. Time flows forward steadily, without effort on your part. You do not need to chase it. You do not need to control it. Each moment will arrive softly, inevitably, carrying you like a current downriver. Let your thoughts scatter now, like starlight bending past the sun. Let them arc and fade until they dissolve into quiet. Let your breath become the only rhythm, slow and even, as the fabric of spacetime carries you gently onward. You are part of the universe's weave, as much as the stars, as much as the galaxies, as much as the light itself. Not separate, not small, but continuous with the fabric that stretches in every direction. All is calm. All is steady. All is rest. Close your eyes a little heavier now. Trust the quiet geometry of the universe to hold you. Trust time to carry you forward. Trust space to cradle you softly. You are safe in space-time. You are safe in the night, and you can drift now into sleep.